Let's go ahead and prove the concavity test, which says suppose that the second derivative exists on an interval. If the second derivative is positive on the interval, then the function is concave up on the interval. If the second derivative is negative on the interval, then the function is concave down on the interval. Those are the two parts we want to prove. Let's start by letting a be any number in this interval. So we're looking at this interval, and we've got some a in the interval. The point of the tangent to the curve at a would be at a f of a. So let's go ahead and write an equation to the tangent to the curve at a. We know that's going to be y minus the y from the point equals the slope, which is f prime of a, times x minus the x from the point. So of course we can express the tangent as f of a plus f prime of a times x minus a. So this is the tangent at a. Now we're going to need to look at a couple of cases. First of all, x is not going to equal a because we know that the function value and the tangent to the curve equal each other at the point of tangency. So we're going to consider two different cases where x is greater than a, and then in a minute we'll consider the case where x is less than a. So if x is greater than a, we're going to look on an interval from a to x, and we can apply the mean value theorem to this because we have that the second derivative is positive. That was our assumption. And then if the second derivative is positive, that means the first derivative exists on this interval, and therefore the function is differentiable on this interval, and therefore the mean value theorem applies. So there exists a c, this is an element of, which is an element of our open interval from a to x, such that f of x minus f of a equals the derivative at c times x minus a. So that's just our conclusion of our mean value theorem. We're going to use that in just a minute, but first let's think about what it means to have the second derivative greater than 0. What that tells us is the derivative function itself on this interval is increasing, because we know the second derivative is the derivative of the derivative function, and we know that if the derivative of a function is positive, the function is increasing. So what I know is the derivative is increasing on this interval. So if I take f prime of a and I take f prime of c, because I know that the c existed right here somewhere on the interval between a and x, I know that the derivative here must be less than the derivative here because the derivative function is increasing on this entire interval. So this derivative must be less than this derivative. I'm now going to multiply both sides of this inequality by x minus a. And this won't affect the inequality because I know that x is greater than a, so x minus a is a positive quantity. I want to do one last thing with this before I start substituting, and it'll be obvious why I do that when I do the substitution. So what I would like to do now is add f of a to both sides. So I've got f of a plus f prime of a times x minus a is going to be less than, we're adding f of a to both sides, so f of a plus the derivative at c multiplied by x minus a. Let's go right back up here, and what if we moved this f of a to the other side? So we had f of a plus, and we moved it here. So the function at x equals f of a plus f prime of c times x minus a. Oh, well that's exactly what I have here. So I could replace that with f of x. I'm going to write that side first. So I have f of x, of course I got to turn the inequality sign if I do that, is greater than f of a plus f prime of a multiplied by x minus a. But hold on a minute, what did I just write here? Oh, look up here. I just wrote down the equation for the tangent to the curve at A. So what I have just proven is the function for any x on this interval is greater than the tangent to the curve. So this will be true for any x value on the original interval I that is greater than A. Now let's look at the case where x is on the interval I, but it is less than A. So we're looking at some x that is less than A. Well, if x was less than A, then we know that the derivative at x is going to be less than the derivative of A, so this inequality sign right here would have to be the other way. But then when we multiplied both sides of the inequality by x minus A, because x was less than A, that would be a negative quantity and we would have to turn the sign the other way. So in the end, we end up with the same result, whether x was greater than A or x was less than A. That result being that the function greater than the tangent to the curve, therefore the function is concave up. Now the test for concave down would be the very same kind of a test. So we could use this very same proof, only we would start out with the assumption that because the second derivative was negative, that our derivative function was decreasing, and just everything else would be analogous.